everybody, this is action potential, otherwise known as the neural impulse. If you think you have this topic down, I suggest to just go to the end of my video where there's a recap for some quick notes, but if you think you need a more in-depth explanation, stay with me. Alright, so action potential. The textbook definition is a brief electrical charge that travels down an axon, but at least in my opinion, this doesn't really explain what an action potential is, so let's get more into depth. So how does this work? Let's start by explaining a battery. So batteries, as we all know, have a positive side and a negative side. They have the potential to release energy, but they don't really do so unless they're used in something, like a TV remote, a flashlight, whatever you're using a battery for. And when these charges are brought together, they create electricity. Yay! So now that we've covered batteries, now let's look at neurons. So neurons actually function pretty similarly. They generate energy from chemical events. So if we were to look at a resting neuron, we can see right here how they're really similar to batteries. We have that positive side, that negative side, and here's the membrane that separates them. So if we want to take an even closer look at this, we can see really what makes up that positive outside and negative inside. We can see that positive outside is mostly sodium and chlorine. And then on the inside, we have mostly these potassium ions. But on the inside, we also have these larger proteins that are negative. So these larger proteins right here are what really make the inside of a neuron negative. A way to remember this is a salty banana. If I were to pour salt on a banana, we all know that salt is full of sodium and bananas are full of potassium. The salt would sit on the outside, creating that positive NaCl that we have, and then the inside is made out of potassium, so that we have that negative K. This positive outside and negative inside is called resting potential. Resting potential likes to sit at negative 70 millivolts. So that means if I put a voltmeter inside here of my neuron, it would read negative 70 millivolts. So this does not happen by itself. It happens through this thing called the sodium-potassium pump. So we can see them. The sodium-potassium pump is where every 2 potassiums pumped into the cell, it pumps out 3 sodiums. So this is what causes that positive outside, negative inside, and the difference in concentration, basically our salty banana. This difference is called the electrochemical gradient, which our body doesn't really enjoy. It really likes balance, like homeostasis. It loves all of that. So our body has ion channels. Ion channels are gates that provide a safe way in and out of the cell. There are many different types, but right now I'm talking about voltage-gated channels. Voltage-gated channels open at some voltages and close at others. When they open, ions diffuse across the membrane. An example of a voltage-gated channel is a sodium channel. These like to open at negative 55 millivolts. So say I was reading my voltmeter again, I would read negative 55 millivolts, and now all of these sodiums would come rushing in into the membrane. So let's make up a little scenario, right? Some channels open and some sodium is let in. So we're here at our resting potential at negative 70, and then we go up, then we kind of go back down. Because not really enough happened. It didn't reach our threshold at negative 55, which is actually a really important number. We're going to talk about it in a second. But for right now, we see this little bump. This is what's called graded potential, which is basically a small change in potential. So it didn't reach that threshold. This threshold is important because of the all or none response. This means that if the inside does not reach negative 55 millivolts, nothing will happen. So essentially, just not enough sodium, not enough stimuli came in to create a whole action potential. So to understand that whole action potential, let's get into the steps. So step 1, a neuron is in resting state when a stimulus occurs and sodium channels open. So if we look at it here, that's going to look like this. We have that resting potential. So then, step 2. If a stimulus is strong enough and it reaches a threshold of negative 55 millivolts, voltage-gated sodium channels open. Remember the all or none response. If the inside of the neuron does not hit negative 55, nothing will happen. but for the sake of our graph, we're going to say that it does. So we have here it's heading up, and then boom, hits negative 55. Once that happens, the sodium comes in through the open channels, and this depolarizes the cell, and it hits positive 30 millivolts. This is the action potential. So if we go over here, it's going, whoa, all of these sodiums are rushing in, and if we look at it through here, we can see how this works. So basically, the change in voltage triggers the next channels to open. So now these will trigger these, and they'll go in. And if we were to read this on our voltmeter, we would read positive 30 millivolts. So after depolarization comes repolarization. This is when potassium comes out and the voltage drops. So repolarization looks like this. We hit that positive 30 and then we're going back on our way down. So it's basically the same thing as depolarization, but with the potassium coming out. So it's going out and out, out and out. And you might be asking, well, what are all these currents doing? Like, are they really doing anything? And yes, they are. So once I have some information over here, right, some neurotransmitters, whatever it is, that needs to be sent to the end of the axon terminal, these charges push this across. So it's like, say I live in an apartment building and I have a trash chute. If I were to drop trash, it like falls through the like trash tube into the dumpster. So we can imagine kind of the same process here. It's going through the tube into where it needs to go for something to happen. So anyways, back to repolarization. So once this happens, it happens so much. Honestly, in my opinion, I think like the potassium they get really excited. So they go a little bit under that negative 70 resting potential. And this is what's called hyperpolarization. So this hyper. When it goes under that negative 70. But then it chills out and it goes back to resting potential. And then once it goes back to resting potential, it starts here with step 1. Again, but something important to note about all of these steps is that the refractory period. So basically, the refractory period is when channels open. During this, the neuron cannot respond to any other stimuli. This is to prevent information from traveling back and forth across the axon at the same time. And I know somebody already did their video on this, but I would just like to quickly mention excitatory and inhibitory. So excitatory would refer to depolarization. So it's like getting really excited, right? And inhibitory refers to repolarization. So our book refers to this as gas pedals on the neurons. Gas pedals on the neurons, right? So the excitatory is like, yeah, pedal to the metal, let's go. And inhibitory is like, no, I kind of want to push the brakes on this one. So this is our action potential graph and what it looks like, and all of the steps if you need to write that down. So again, this might be a little bit confusing because it's like, okay, well, what is this all for? This is to get information across. So once our information is here, right, this is resting potential. So our information is in this area, like kind of the dendritic cell body during resting potential. And then it comes over here during graded potential, and action potential is when it gets pushed across that axon. And you might be asking, well, does it vary by speed, strength? Like, what's the deal with this? So they actually can vary by speed, but the speed does not rely on the stimulus. So it does not rely on stimulus. Very important. Stimulus can only impact frequency. So, but anyways. So it does not rely on the stimulus. It varies by speed because of the myelin sheath. Some neurons are insulated and some are not. When a neuron is insulated with myelin sheath, it means that the neuron's transmission is sped up. This is because the current jumps from node of Ranvier to node of Ranvier instead of one channel at a time. they can differ from 2 to 200 miles per hour. So places like your reflexes are going to have the fastest, and places like your guts are probably going to have the slowest. And yeah, that's action potential. Now it's time for the quick recap. So, neurons transmit messages when stimulated by our senses or by neighboring neurons. These messages are sent by firing an impulse called the action potential. Our resting neurons are basically salty banana batteries. They generate electricity from chemical events, and they have that negative potassium on the inside and positive salt on the outside. This is orchestrated by the sodium-potassium pump, which means 2 potassiums in is 3 sodiums out. And this kind of difference that this creates is the electrochemical gradient. And does our body like this? Yes or no? No, it does not. So it has ion channels, other ways for these ions to get in and out of the membrane. And then finally, we have our actual action potential. Negative 70 millivolts is that resting potential. Negative 70 to negative 50 is graded potential. Positive 30 millivolts is when our graph is going all the way up and it's depolarization. All of the sodium is rushing in. Negative 55 millivolts is when our graph is going back down. It's repolarization, and all this potassium is coming out. And then finally, we have that below negative 70 is hyperpolarization. The potassium got a little bit too excited. So, two things to note with this is that all or none. If it doesn't hit negative 55 millivolts, nothing will happen. And then our refractory period. When channels open, the neuron cannot respond to other stimuli. Finally, our information during resting potential. It's here. The info during graded potential is here. During action potential is here. And these are the myelin sheaths. They make it go faster. Yay! All right. These are my citations and my honor code. Thank you so much.